Applications of periodic functions. Okay, let's see where we can actually find some of these mostly sine and cosine functions in real life. And we'll start off with a scenario that's pretty neat. Um, let's take a look at a Ferris wheel, and not just any one. We're going to go down to Las Vegas and take a look at the high roller. It's called the Link or Lynx Ferris wheel. Here's an artist's sketch of the Ferris wheel above the Las Vegas skyline. You can see it is pretty tall. And on the edge of the Ferris wheel, there are not just seats, those are actual pods. And let's take a look and see what one of those pods looks like. Again, an artist's sketch of one of the pods, which is a little cooler than just a regular seat. So it looks like you can maybe even do a little gambling while you're in there. You can certainly get some maps and things of what's going on. But you're stuck inside this pod for a half an hour at least that it'll take to go around the entire Ferris wheel. If that's the case, if you only go around once, it would be an hour if you end up going around twice. So here's some information about that Ferris wheel. So our first example, the Las Vegas High Link Roller Ferris wheel, and it has a radius of about 275 feet, and it rotates one time around every 30 minutes. Riders enter the pod at the lowest point of the Ferris wheel, which is about 10 feet above the ground, and I'd like to find, there's two parts. I'd like to first find a sinusoidal function that gives the rider's height h after t seconds of motion. And part B, I want to find when the rider first reaches a height of 100 feet. So to build a sinusoidal function, and sinusoidal means wave-shaped, and so we can use a sine or a cosine graph, whatever is easier to do for this function. But to come up with this sine or cosine function, it's easiest to start off with a couple of pictures. First, a picture of what our roller coaster looks like. Our Ferris wheel looks like. So the Ferris wheel is approximately a circle, and at a height of 10 meters, people get into one, or 10 feet, people get into one of the pods. So this part's 10. And then the distance from here to here is the radius, and the radius in any direction is 275 feet. And then there's one other important piece of information we've been given, and that's that it takes a certain amount of time, in this case 30 minutes, to go all the way round. Now, if we want to do this in seconds, which it asks for, then I need to think about 30 minutes in seconds, and so each minute is 60 seconds, so it's going to take 1,800 seconds for this Ferris wheel to go all the way around. So once you've got this, and you know up and down this way is 275, down this way is 275. Once you've got some of this initial information, you can start to sketch what the sinusoidal graph looks like. So if I give myself a little bit more space here, and I create a graph, and in this direction we'll use time, and that'll be t. And in this direction we'll use height, and that'll be in feet. This will be in seconds. So when the rider first gets on at time 0, they will start above the ground. They'll already have to climb some stairs or something, and they'll be 10 feet off the ground. And then we know that they'll end 1,800 seconds later. They'll be back to the beginning. They'll have gone through one complete cycle. And if I sketch in this cycle, I know that it has to be wave-shaped. I got that hint from the beginning. It's a sinusoidal function. And I know all sinusoidal functions are the same on each side of it. So halfway down the middle here, it would reach its peak. That would be at 900 seconds because of its symmetry. And I know that this distance and this distance here will be that 275 and 275, which is 550. So the top that you'll get to, The highest elevation you'll ever get to is 560 feet. The 10 feet that you started off, plus 275 as you go up, and then 275 more as you get to the top. And it's going to be important where this midline is, and that midline is at 285 feet. 275 and 10, 285 feet. And that's where these 2 points would occur. So I'm actually pretty close to being able to complete this as a sinusoidal function that gives the rider's height h. So the rider's height h at time t will be equal to, and now I need to start putting some things in. And the very first choice is to work out whether or not you want to do this in terms of sine or cosine. To me, this looks more similar to a cosine graph than a sine graph, so I will start with that one. I can show you how to do both, but I'll start with that one. So if this is a cosine graph, then the amplitude of the cosine graph has been multiplied by 275. So now the wave goes up and down 275. And the cosine graph's also been flipped over. Normally a cosine graph starts high, goes low. This one starts low and goes high. So I do need a negative sign. So this is the amplitude, essentially. Then I need to figure out phase shifts and vertical displacements and what the period is going to be. So let's work with the period next. Normally it's 2 pi over b. That's what the period is. And I know that in this case the period is 1,800 seconds. So therefore b, so a little bit of algebraic manipulation. Multiply this side by b, multiply this one by b, and I get 2 pi is 1,800b, divide by 1,800, reduce 2 and 1,800, and I get pi over 900 is my b value. So this is going to be pi over 900. Then I think about the x value and the phase shift. Well, this hasn't been phase shift left or right at all, so this is just x when I'm dealing with the cosine graph. Then I need to displace this, and it has gone up 285. That's where we need this midline, where it becomes really important to be able to find that. So the whole graph's been moved up 285. From there it goes up 275 and down 275. Okay, I have my function. So if I wanted to do this with a sine graph instead, I'd still have h of t. The sine graph would still have 275 as the amplitude. Now it's in terms of sine. The period, I would have worked through the exact same work to get the period of pi over 900. But now there's a phase shift, because a sine graph starts on the midline, goes up, down, and then back up again. So my phase shift is I've moved it to the right. So to account for that, I need to move it to the right. And the amount that I've moved is exactly 450. So minus 450, I'm still up 285. And this is a plus sign in front because I haven't flipped the sine graph. There are a lot of other answers that also work. However, this is probably the easiest one to find in terms of sine, and we've already done one in terms of cos. So we've completed the first part of this question, which was to find the sinusoidal function that gives a rider's height after t seconds of motion. And now we need to move on to finding when the rider first reaches a height of 100 feet. So I'll show you how to do this in a couple of different ways. We'll do it graphically first, which is fairly easy, and then we'll do it algebraically second. To do it graphically, I'm going to need a graphing calculator. So let me grab one, and we'll do it that way first. So we need to go enter in our function. So negative 275 cosine of pi divided by 900 times x. close those brackets off and add 285, and then we should go into our window settings. Don't just hit graph. Go into the window settings and think about what the windows are. So in the X direction, we really want to make sure that we're going from 0 to 1800, and I've already entered that in with a scale of maybe 50 or 100. That's how often to put a little tick mark along the axes. And in the Y direction, the height go from say 0 to say 600. You could just go to 560, but to go a little bit above is nice. And again, I picked a scale of make a little tick mark every 50. And now when I graph, I should see that I start basically really close to 0, and I'll end really close to 0. Now I go back into y equals, and I create a second line at y equals 100. And so that's making a line at height is 100. And when I graph that, I get this sort of picture. And at that intersection point, this intersection point here, that would be one solution for when I reach 100 feet. And that's what we want to find when the riders first reach that height. And you can do that by calculating. So second function, calculate, and number 5 is the intersection. And it asks you where the curves are, so yes, that's the first curve. And although this isn't a curve, that is the second equation. And then give it a guess. You don't have to go too far over, and I'll explain next year in calculus why not. Once you make that guess, it should find the intersection point is 238.6 seconds is the first time you get there. The graphing calculator has stored that value as of x. So if you quit out of your graphing mode and you ask it what x is, it'll remember that value. So if you want to know how many minutes it is, you can just divide it by 60 and get approximately 4 minutes is how long it takes to get to a height of 100 feet. Alternately, we can do this question algebraically. So let me show you how to do it algebraically. First of all, I know that the height's going to be 100. So I can start with that. And I need to solve for this x. So I'm going to have to slowly solve for x. For instance, first I could subtract 285 from both sides. So negative 185 would be negative 275 cos of this complicated angle. Divide both sides by 275, and I get a decimal place of about 0.6727. So I am using a calculator to help with some of this, but I am doing it from a much more algebraic approach. This is this value. Now, this is where it gets a little bit tricky. I'm going to make a substitution. Instead of solving for this complicated thing, I'm going to call that complicated thing, instead of pi over 900x, I'm just going to call that theta. So really what I want to solve is this question. And hopefully you can see that that's fairly easy to solve. If you've stored this 0.67272727 on your calculator, all you need to find out theta is just do inverse cos of that number on your calculator. And you should get a value for theta that is approximately 0.8329, and there's a lot of other decimal places, so I might want to use the storage feature on the calculator. And now I know theta, I can figure out x, and x is just 900 times that theta all divided by pi. And so again, I grab my calculator and I calculate what this is, and I get approximately 238.6. We won't worry about too many decimal places, and technically this is actually t, not x, and t is in seconds. And does it make sense? Well, let's take a look at our graph one time and see if the first time you would hit 100 feet would be about 238 seconds. So 238 seconds would be in here somewhere, and yeah, that certainly looks approximately when you'd hit 100 feet. So I'll assume that that's the right answer. And generally we don't talk in seconds, so you might want to convert this to minutes simply by dividing it by 60, and so it's about 4 minutes. So at approximately the 4-minute mark, you hit the 100-foot mark on this roller coaster. So it does take quite a while to lift you up. It's not going super fast, which confirms what we saw when we did it graphically. Okay, let's take a look at another example.